13th episode. The number 13 is a special number. But today also we have a special subject, average ship thickness. I remember back late 70s, beginning 80s, this was a very hot thing, you know, in machining, ship thicknesses, average ship thicknesses. And then till mid 80s, beginning of the 90s, everybody was talking about it, and then it seems to, it disappeared from the table. So the question for today is it gone? We don't need it anymore? It's an outdated subject, or what? Well, again, welcome at this episode of Getting Technical. Together with my colleagues working behind the camera, we will try to make an interesting session for you today on an interesting subject. The big challenge for me personally today is to keep it limited to 40 minutes, because I think this is such an intriguing subject, such an interesting subject, average ship thicknesses. And why is that so important still today? And I hope to convince you that still today this is something we should think about, we should work with. But first a flashback. You remember last time we were talking about something we called milling cutter positioning. The subject was, how do we position a milling cutter and a workpiece compared to each other? How do we let them move? And we kind of said there are three possibilities. There is side milling, up milling, central milling, and side milling, down milling. That are basically the three things we can select from when we talk about positioning. And we talked about it, and we talked about exits and entries, and how ships are formed, and vibrations was a subject. And we kind of came to a conclusion that option C in this picture, side milling, down milling, for the performance of the milling cutter is best. But at the same time we said, or perhaps I didn't emphasize enough, but option C, side milling, down milling, we also defined it as the cheapest one, giving longest tool life. Highest productivity. Now, why highest productivity? Why should option C be faster than option A or option B? The workpiece has a certain length. The milling cutter has to move from point A to point B over the workpiece. The milling cutter is milling with a certain table feed, the speed with which the milling cutter moves. The distance to travel is fixed. The speed with which the milling cutter moves is fixed, isn't it? So the time to do operation A or operation B or operation C is the same, isn't it? So why do we dare to say here that operation C is more productive? And please give me your feedback. Put it in the chat here. Put it in the comments here. I'm very interested to hear from you in this matter. Why do we say operation C is more productive than operation B or operation A? That's the question here. And in the invitation for this event, I put a sentence. Kind of, if the machinist would use the milling cutter in the same way as what the designer of the milling cutter was thinking on when he or she was designing the milling cutter, that would make sure that all the potential in the milling cutter is maximized in the workshop. And the subject of average ship thickness is just about that. How can we make sure that the typical things a designer of a cutting tool, a designer of cutting edges, of carbide grades, of cutting geometries is thinking on? How can we make that the operator in the workshop knows about it and works within the same frame? That's what we are talking about here. And what exactly are we talking about? And here I need to clarify a bit, because here it can be a bit confusing, because there are two things here. If we talk about thickness, there is thickness of the so-called undeformed material. In the video you see here, the symbol used for it is H1. That's the thickness in the feed direction, the thickness a cutting edge is going to cut. Next to that thickness of the undeformed material, measured perpendicular to the cutting direction and to the cutting edge line, there is also the thickness of a ship. And we always talk about the thickness of the thickness of the ship. Here the symbol used is H. And then it starts perhaps a little bit confusing, because H is the thickness of a ship, while all the models, all the things we use in machining to define how a cutting edge is functioning, to understand what physical phenomena are taking place on a cutting edge, everything relates to H1. So, and here the confusion gets started, because we talk about ship thickness, but using the word ship thickness, we think thickness of the undeformed material, which is H1. And that is kind of an agreement we need to take here together, that if we use the word in the English language, if we use the word ship thickness, and later on average ship thickness or equivalent ship thickness, we come directly to those things. But if we use the word ship thickness, it's not actually the thickness of the ship we talk about, but it's the thickness of the undeformed material just before it's being cut. And you know, as far as I know, there are only 2 languages in the world where this confusion is not happening. I don't know if there are people here listening that talk Dutch as their native language, or German. Because in Dutch, what we call in English ship thickness, in Dutch we call it verspanningsdikte, the thickness of the material just before it's being cut. In German we talk about the Zerspannungsdicke, which is exactly the same thing. But anyway, we talk English here, so let's stick to that. We talk ship thickness, we say ship thickness, but we should think in terms of thickness of the undeformed material just before it's being cut. And that ship thickness, and from now on I talk ship thickness, there are limits. Like always in machining, there are limits. There is a minimum and a maximum. And you should think like that if the thickness of the material you want to machine is too high, if the thickness is too much, you are going to have problems with the cutting edge during machining, because mechanically the cutting edge is going to be overloaded. The cutting forces are going to be too high. The mechanical pressure on a cutting edge is going to be too high, and that will lead to fracturing of a cutting edge, breakage of a cutting edge, with other words, premature reaching the tool life. So ships should not be too thick. And again, it's the last time I say for today, but remember, ships should not be too thick means the thickness of the material you are going to cut should not be too thick. Too thin a ship is also no good, because the ship is the major vehicle we use during machining to evacuate heat away from the cutting zone. And to be able to do that, the thicker the ship, the thicker the material we cut, the bigger the volume you have of material with which you can take heat out of the cutting zone. If you make ships thinner, you have less volume of material being removed, so you have less ability to take heat out of the cutting zone. Too thin ships could lead, well, to a thermal overload of cutting edges. And if you have thermal overload, again, you will suffer from problems with premature end of tool life. Because now it's not due to mechanical loads, it's thermal loads that are going to in a thermal way, overload the cutting edge, burning the cutting edge, kind of. And that will lead to short tool life. So a correct chip thickness, not too thick, not too thin, gives us a balanced load, both mechanical and thermal on the cutting edge, and that on its turn is what we need to have a predictable, a stable tool life, and that is what we need to have sustainable machining, that we control the thing, that we can predict what's going to happen. So chip thickness is in machining an important cutting condition. And it's important to realize that, because now I have to ask all of you to take perhaps a very serious step, and that is that we have to be aware from now on that if we talk about cutting conditions in machining, there are kind of two levels we can talk about, we should talk about. One way of talking about cutting conditions is to talk about feeds and depths of cut and cutting speeds. Those cutting conditions very often are referred to as the workshop cutting conditions. Because if you listen to the definition, take for instance the feed. The feed is the speed with which a cutting tool moves along the workpiece. So it seems that the workpiece is the reference. Feed is how fast as a tool moves along the workpiece. Depth of cut is the thickness of material I remove from the workpiece. The cutting speed is the speed with which the workpiece rotates in case of turning. So it's all about the workpiece. Those cutting conditions we refer to as workshop cutting conditions. The other set of cutting conditions, also referred to as the technological cutting conditions, refer to the cutting edge. The cutting edge is your reference. And then we talk about the thickness of the material that the cutting edge needs to cut. The chip thickness. Careful again, remember? Chip thickness, symbol H in the picture here, which is the thickness of material a cutting edge is going to cut, and it's measured perpendicular to the cutting edge line. So the cutting edge becomes now my reference. There is also something we refer to as the chip width, symbol B in the picture here. And B is the width over which a cutting edge makes contact with workpiece material. So on the one hand, now we have the feed, symbol F, and the depth of cut, symbol AP, the workshop cutting conditions. And from a technological perspective, from a cutting edge perspective, to understand what's going on the cutting edge, actually, we talk about B and H, width of cut, chip thickness. And a major parameter there that influences the relation between these things is the cutting edge angle. The cutting edge angle being defined as the angle that between the cutting edge cutting and the feed direction. And you see here three possibilities. You see to the left 90 degrees cutting edge angle. You see in the middle roughly 60 degrees cutting edge angle. And you see to the right 45 degrees cutting edge angle. The values here are not so important. It's just more for your information. But what you see is that if the cutting edge angle moves away from 90 degrees and you have a set of workshop cutting conditions I consider as being stable, I'm back, it seems. You know, the big lady behind these things is a girl called Alesia. You see her top right. In preparing for this, we were talking about number 13. Getting technical, live event number 13. Is number 13 a good idea? Shouldn't we be skipping 13 and go directly to 14? But Alesia told me she's not superstitious. But anyway, you see number 13 hit us. Now I try to go back where we were before. I see the picture is a little bit mixed up, but that comes back to the normal situation. We were talking about cutting conditions, workshop cutting conditions, technological cutting conditions. Workshop cutting conditions are the cutting conditions that we use in the workshop, that we use to program the CNC machine. Its depth of cut, its feed, and its cutting speed. And normally, traditionally, these things are fixed. Once they are determined for a certain workpiece, for a certain cutting tool, that's how we program them, and that's it. The cutting edge itself, how a cutting edge works, the physical phenomena that are going to happen around the cutting edge, the wear we will see on a cutting edge, the tendency for vibrations and things refer to the technology or are influenced by the technological cutting conditions. The width of cut and the chip thickness. And there are more than one variable that determine the relation between, on the one hand, the feed and the chip thickness, because there is a relation between those two. And on the other hand, the width of the chip and the depth of cut. And here in the picture you see just one example. The variable we try to illustrate here is the cutting edge angle. A cutting edge angle of 90 degrees, 60 degrees, and 45 degrees. And we see that if a cutting edge angle moves away from 90 degrees for a given feed and depth of cut, we consider those fixed now, we see that the chip in cross-section is getting wider, the B value increases, the width over which the cutting edge cuts is getting bigger, but at the same time, the thickness of the chip, and remember what I said a couple of slides ago, it's not the chip itself, but it's the thickness of the undeformed material just before it's being cut. The thickness of a chip is reduced. This phenomena often is referred to as chip thinning. And now and then I end up in serious discussions because a lot of people consider chip thinning as a very positive thing. People say, you know, high feed machining, it's due to chip thinning that we can do high feed machining. And that's absolutely a correct statement. But there are limits. As I said a couple of minutes ago, if a chip is getting too thin, you end up in another potential issue. That is that you can't evacuate the heat. So that whole chip thinning thing, be a bit careful with it. There are limits to how far you can take it. And in milling, there is one thing that makes life a little bit more complex even, that is, imagine, and I try to illustrate it here with an animation and with a real-life video. In milling, and you use a milling cutter with a certain feed per tooth, feed per rotation, table feed, whatever, how you define the feed, and that's a fixed value. Well, the thickness of a chip cut by each and every cutting edge is constantly changing. A cutting edge starts cutting, in the examples as you see here, starts cutting with a thickness of 0. And then the thickness of the chip is increasing. It reaches a certain maximum value. And then it's decreasing again to end up at 0 again, if the milling cutter is cutting over its full width. And now we have a dilemma. The dilemma here is, as I just said, the chip thickness is a measurement, is a metric to understand how the cutting edge is functioning from a physical perspective. But in case of milling, where the feed is a fixed value, that chip thickness is constantly changing. And that is the dilemma, second half of the 70s or even before, but it really took a very high flight, second half of the 70s, beginning of the 80s, that people started really to think about this. And that was roughly when people started to use carbide and as a cutting material and insert type milling cutters, because then suddenly it became a bit more important than before. That dilemma we have in milling, where while a milling cutter is machining, and you see here a milling cutter fulling cut, the radial depth of cut equals the diameter of a milling cutter, and the milling cutter is moving with a certain feet per tooth, feet per rotation, table feet, whatever how you define it. Well, in such a case, the thickness of a ship starts at 0, which could be too thin, see heat and stuff. As the milling cutter continues rotating, the thickness of a ship is going up. It reaches somewhere a maximum value, which is perhaps too big. Think on mechanical loads and braking and stuff like that. And then the cutting edge, as it continues cutting, the ship thickness is going back to 0, perhaps again too thin, and think on heat. And that's the dilemma with which we are confronted here now. How do we make it happen? What I said a couple of slides ago, how do we make it happen that the things the designer of a milling cutter is thinking on, and designer of milling cutter, they think on physical phenomena, they think on ship thicknesses. How do we connect this in a practical way to people in a workshop that work with feet? And how do we make that the feet which is selected to use the milling cutter with is not jeopardizing ship thicknesses too big, too small compared to what the designer of the milling cutter was working with? That is what we are focusing on here. And to make it, remember, we talk second half of the 70s, beginning of the 80s. We had computers, but limited. So it was more in those days about a practical manner, a practical system, a practical approach to connect variable ship thicknesses with fixed feeds in a way that it makes sense, in a smart way, in an intelligent way. And to make that happen, we said, okay, we are confronted with a situation. A milling cutter is working with a certain feet. Take here feet per tooth per rotation, Fz. That leads to that a cutting edge is going to cut a ship with a thickness, with a cross-sectional thickness, which you see here, which is the gray zone limited by the red lines. That's the section of a ship. And the thickness of that ship is changing constantly from a certain maximum value to a certain minimum value in the example as given here, which is down milling. Well, we kind of invented, I could perhaps say, something which we refer to as average ship thickness. Average ship thickness is defined as, imagine you create a theoretical ship, and that's the first important word, theoretical, because sometimes people ask, where do I measure average ship thickness? Well, I have to disappoint you. You can't measure an average. It's just in our head. And I know practical people like to measure. I'm sorry to have to disappoint you here, but it's just something we use to think, to calculate a little bit with also. Average ship thickness, we create a theoretical ship with the same length as the real ship. The theoretical ship is the blue ship in the picture here. The real ship is the gray ship with the red surrounding lines. A theoretical ship with the same length. Why do we want to have the same length? Well, we want to have the same time in contact when we think in terms of tool life and stuff like that. So the theoretical ship should represent the same time in contact as the real ship. And the cross-section, the surface, should be the same as the real ship. Why do we want to have the same surface? Because we want in average to have roughly the same mechanical loads acting. The thickness I need to give to that theoretical ship so that thickness multiplied with length equals surface, that is what we refer to as the average ship thickness. It's a pure theoretical thing. It goes back to late 70s, beginning 80s, an era where computers were not so well spread yet. And we had the ambition that the designer of a cutting edge and the user of a cutting edge somehow should be in contact with each other. What the designer of the cutting edge was working with to design the cutting edge concerning loads and stuff like that, and the cutting conditions used by the user in the workshop, the feeds and the depths of cut, should be as such that what the designer defined is respected. But we did it in how should I say this now, a friendly manner, and we created an average ship thickness. Just in between, for those who work with solid carbide milling cutters, did you ever wonder if you have a solid carbide milling cutter, and if you look to the wear on cutting edges, that the wear on the actual cutting edges will be always less than the wear on the point of the tool? And in 90% of the cases, if you have breakage of solid carbide milling cutters, the initial breakage, and I don't talk here about a crashed milling cutter, because CAM programming, there was a mistake or something, but normal breakage due to machining, that it always initiates at the point. And why that is? Because there must be a reason for that. And in that respect, I would like to draw your attention to a Swedish gentleman who, he wasn't talking, he wasn't thinking about solid carbide milling cutters, but afterwards it seemed that what he developed as a concept was the explanation why solid carbide milling cutters always wear out first at the point, and it's called the Woxane model. Woxane was a Swedish professor, and he was thinking on how actually cutting edges function, and that also the point is cutting. And what Woxane identified is, and that is the picture to the left here, the light gray zone represents the cross section of a ship being formed, A, the symbol here is, and what we see is that if you come closer to the point of a milling cutter, the real ship is getting thinner and thinner and thinner to end up in the end at zero. And at the point of a cutting tool, we have a situation where the ship is too thin, it can't evacuate the needed heat anymore, the heat stayed concentrated there where it's generated at the point of the tool, and it burns the tool. And in the same, as that is the explanation, at the same time Woxane was thinking about this, how can I somehow compensate? And he did exactly the same thinking as what we did in milling. He said, you know what, I'm going to replace the real ship, the light gray ship here, by a theoretical ship, the dark gray ship here, again with the same length. So the same length of the cutting edge, point included, is in contact with workpiece material. I give it the same surface. So it represents kind of the same load in average over the cutting edge, but I give it a rectangular shape. And the thickness of such a theoretical ship, Woxane defined as the equivalent ship thickness. Interesting that in two situations people followed kind of the same way of thinking. And you know, in milling today we talk about equivalent ship thickness, and also here I want to mention this because it's very important to realize that what we call average ship thickness, and I already defined it, and you have equivalent ship thickness, see the Woxane model. Well, there is a gentleman, Søren Hägglund, and he worked on these things and he combined the two. he took average ship thickness as defined in milling technology. He took the Woxane model and he brought the two together. And that is what we call today equivalent of the milling equivalent ship thickness. It's a Swedish gentleman, Søren Herlund, who did quite a lot of pioneering work in bringing these two together. And some of you perhaps noticed that if you use the Suggest software we from Seco make available for everybody, that there we talk about equivalent ship thickness and no longer only about average ship thickness. As with this, you know the background of this. Now the variables in this thing, you have average ship thickness, you have, or equivalent ship thickness I should say, you have feeds and speeds in the workshop. How do the two relate? What do we have to take into consideration? And I give you some examples. What you see here is two milling cutters, the same diameter. Both milling cutters are working, however, in a situation to the left you have a big radial depth of cut, to the left, to the right you have a small radial depth of cut. And you very clearly see, both milling cutters are used with the same feed, that the ship as being formed, the dark gray zone surrounded with the red lines, in the left situation, the average ship thickness of that ship is bigger than the average ship thickness of the ship which is formed to the right. So somehow the relation between feed and average ship thickness is influenced by the radial depth of cut. At the same time, you can see these two pictures as being drawn with a different scale. And the scale is as such that the radial depth of cut left and right is the same. With other words, right, you have a milling cutter with a much bigger diameter. And then I can tell you exactly the same story. So it seems that big radial depths of cut make ships thicker. Smaller radial depths of cut make ships thinner. Bigger diameters of milling cutters make ships thinner, and smaller diameters of milling cutters make ships thicker. That are elements we have to think about. Another thing we need to take into consideration is milling cutter positioning, the subject of last time. Milling cutter positioning, you see here central milling and you see here side down milling. Again, one milling cutter, same diameter, same feed. The feed per tooth is the same. In case of central milling, we see a ship which is thicker average than the ship which is being formed when a workpiece is put sidewards compared to the milling cutter. That means that the milling cutter positioning influences the relation between feed and average ship thickness. Another variable we need to take into consideration, another yet one we already mentioned, is the cutting edge angle. You see here three examples: a cutting edge angle 90 degrees, a square shoulder milling cutter 45 degrees cutting edge angle, a typical surface milling cutter, face milling cutter, sorry. And to the right you see 30 degrees. That kind of represents high feed milling cutters. You see all three used with the same feed. And you see, as you move away from 90 degrees, you have a thinner ship for the same feed. So the relation between the feed and the chip thickness is also influenced by the cutting edge angle. Also important to be aware of is that if you have different types of cutting edge geometries, a subject we once talked about, and next time we are going to talk quite intensively about this also. If you modify the cutting edge geometry from sharp to strong, that means that to make sure a cutting edge is well functioning, you need to modify, you need to adapt the chip thickness to that. A certain cutting edge determines a certain thickness of workpiece material needs to be cut as for the cutting edge to behave normally. That means that there is also, if you have a certain type of cutting edge, you need to be aware of that a certain type of cutting edge geometry demands for a certain average chip thickness. And that is represented in for example, in diagrams like this, that for sure you have seen already. Here you see examples from milling cutter cutting edge geometries. And you see a number in each of these designations. Well, the number indicates that this cutting edge with a very typical geometry, whatever it is, should be used with a specific average chip thickness. The difference between an ME11 and an MD18, as an example, the MD18 is a much stronger geometry, but to make it fully work, it also needs an average chip thickness of 1800ths of a millimeter, where an ME11 is a much sharper geometry, and you can go down in average chip thickness. You can go to 1100ths of a millimeter. So the cutting edge type you are using and the average chip thickness you are using, yeah, there is a relation between that. And for sure, people then say, yeah, but wait a second, this for sure is influenced by the workpiece material you machine. And of course it is. That's why if you find advice like an MD18, it says that you should use an average chip thickness of 1800ths of a millimeter, but that is true when you machine steel. When you machine different types of material, depending on the properties of the material, you should increase or reduce that value a little bit. And that is what you find in diagrams or tables or pictures, I don't know how to call this, like this, where we say, okay, if you use an MD18 and you use steel, the P materials, of course you can use that advice. But if you would use the same geometry in hard steel, for instance, H materials, even that strong geometry, you have to be more careful with the chip thicknesses. And that's why it says here in the diagram, you should take that 1800ths of a millimeter and take only 60% of it. That's to compensate for workpiece material properties. And that are the variables: radial depth of cut, diameter of the milling cutter positioning, the cutting edge you use, the cutting edge geometry you use, the workpiece material in which you machine. That are the variables that we need to take into consideration to describe, to define the relation between the average chip thickness, the designer of a milling cutter, and the feet, the user of a milling cutter. And you know, for a long time, people have been focusing on the calculus, on the formulas. And I still remember when I was teaching 20 years ago, hours we spent on this formula, helping people to how to use this, to make the calculations. Again, bear in mind, we talk about end of the 70s, beginning of the 80s, computers and stuff like that was not so well known. A formula like this today is a little bit, no, not the formula, I should say, is outdated, but using the formula for manual calculations is a little bit outdated. So let's not spend too much time on it. As that formula was a bit complicated, people determined simplified calculus. You see here an example where we say, okay, if the radial depth of cut is smaller than approximately 30% of the milling cutter diameter, and if the workpiece is positioned sidewards, down milling, well, the rather complex formula you see on the previous slide can be brought back to this simpler formula. Although a square root and things, I don't know if this is really simpler to use in a workshop, but anyway. To make it even simpler, people had, were provided diagrams like this, or tables like this, where, okay, all the calculation was done, and you just had to follow a certain scenario through this table to find out, in a certain situation, for a certain wanted average chip thickness, which feet to calculate, or which feet to use. Here, of course, very typical for a table is that you need to make estimations here and there. And yeah, in this table you also have the blue column here, but I'm going to let that pass for today, and I'm going to come back to this blue column later on. In May, I think, we have a session on what is called compensation principles in machining. And then I'm going to talk about the blue column in this diagram, the so-called speed factors in machining. Diagrams, graphs, which is yet another way of showing the relation. Here we say the feet you should use is the wanted average ship thickness, corrected with 2 correction factors. One correction factor you can read on the big diagram that takes into consideration milling cutter positioning, central mill and contour milling, side milling, and the radial depth of cut relation to the diameter. The small diagram takes into consideration the cutting edge angle. That's yet another way of working with this thing. Today, of course, computers are very well spread. I should say, don't worry too much anymore about the calculus, about the formulas and so on. Use the means of today for this. For me, much more important today is that we do smart usage of it. It's not about calculation anymore. It's about having insight in this. And I take a few examples. At previous Getting Technical live events, we already talked about things like that. But now we are going to be a little bit more concrete in answering the why and the consequences. If you have a milling cutter and if you do contour milling and you come along a wall and the milling cutter while cutting is suddenly entering in a corner, you are confronted suddenly with a situation which we can define here as we say the radial depth of cut is getting bigger. And everybody sees that. And then people say, yeah, what should I do with that? And then you find here and there some advice, and it says if a milling cutter enters in a situation where the radial depth of cut is bigger than the initial radial depth of cut, you have to reduce the feet. And machining people are sometimes so nice, you know, they believe everything you say. Okay, we reduce the feet. But why do we reduce the feet? Now, with the subject of today, now it should be clear. Because radial depth of cut compared to the diameter is one of the variables that interferes, that determines the relation between average ship thickness and feet. Now, a milling cutter, in whatever situation it is, an average ship thickness is an average ship thickness. That should be kept constant. But the feet should be modified if needed for, and here there is a need to modify the feet because the ship is getting thicker. Too thick, and we have to thin the ship to make the ship thinner, and we do that by reducing the feet. The why answered. A question. Circular milling, the simplest situation there is in non-linear machining. Imagine you have internal and external circular milling. And the diameter, the finished diameter is the same, the dotted line here. And the material oversize, see the red arrows in the picture, is the same. So I have one milling cutter, the same milling cutter. I use it internal, I use it external to produce the same diameter, to remove the same oversize of material. My question is, and I really am looking forward to afterwards to see in the comments in the chat related to this, your answers. Do you think that the internal time to do the full operation is shorter than the external machining time? That is option A. Do you think the 2 times are the same? That's option B. Or do you think the time for internal machining, the machining time internal, is bigger than the machining time external? And internal, same milling cutter, same finished diameter, same material oversight. Internal machining is faster than external machining. It's the same, the time. Or internal machining takes longer than external machining. Option A, B, or C. If I take the 2 apart, it looks like this. And again, I could ask the question, is internal faster, the same as external, or slower? If the diameter we machine is the same, and if the material oversize we have to remove is the same, and the milling cutter is the same. to fully appreciate this, of course, you have to bear in mind what we have been talking about already 2 or 3 times now, that you correctly apply the definition of feed. Feed is movement of the center line of a milling cutter. To the left you see linear machining, in the middle you see circular machining where the feed is correctly applied. The center line of a milling cutter, what you see to the right is the situation still so often used where the feed is put at the periphery of a milling cutter, which is of course, and now you should understand much better, I hope, in the situation to the right, the ship is much too thin. You're going to burn the milling cutter. Now, talking about these things, that is, and applying, more important, applying these things, that is what people refer to today as dynamic machining, dynamic milling. Dynamic milling is a situation where we use the calculation power of nowadays CAM systems and machine controls. We use the possibilities we have, and we, much more flexible than ever before, we create a situation where we say, okay, I modify the situation of a milling cutter in such a way that I have balance, and I make that happen in such a way that I modify my cutting conditions, second by second kind of, if needed, so to make sure that cutting edges are functioning well. What we do here, and we are not yet there, but we start to be close, is that we forget about the feet. We say feet is of minor importance, and we focus on ship thicknesses, and we make sure that every moment in time I have the most favorable ship thickness on my cutting edge, or ahead of my cutting edge, and I make movement and speed of movement of a milling cutter in such a way that things are in the best possible way. Kind of, it's reversing the situation. In the past, we said we have a fixed feet, and we accept that the ship thickness changes all the time. Today, more and more, we say, you know what? We want to have our ship thickness as constant as possible, and we modify the feet. And that is possible with the equipment we have today. A little bit later, but that was due to the interruption, the summary, I started with saying if the criteria used by the designer to design a cutting edge, to design a milling cutter, and the cutting conditions used by the machinist in reality in the workshop, if those two would be connected, that would truly assure that whatever possibility built in a milling cutter would be fully exploited during machining. And this is really what it's about. How to proceed, that I exploit the possibilities which are built in a cutting edge as much as possible. And that is possible, but then we have to take as guidance the criteria used by the designer of a milling cutter, and that is what we have been doing, talking about ship thicknesses, feet, average ship thicknesses, equivalent ship thickness, and in the end, dynamic milling principles. In a nutshell, it says, or the way of thinking should be that if the radial depth of cut or the diameter of a milling cutter is changing, and most of the time we work with a ratio here, people talk about the AEDC ratio, the radial depth of cut divided by the diameter of a milling cutter. Well, if that radial depth of cut, milling cutter diameter ratio is getting smaller, you can compensate that with bigger feet to keep the balance between the average ship thickness and the chip thickness and the feet. Small AEDC ratio mean big feet. Of course, the opposite is also true. A big AEDC ratio should be compensated with lower feet, smaller feet. Milling cutter positioning, single-sided milling cutter positioning gives you the possibility to increase your feed. Central milling also means that you have to reduce the feed. And now I come back to my situation A, B, and C. Of course C is more productive. Of course positioning C is faster because you can use a bigger feed. Then in situation B, the central milling I showed you in the beginning of this presentation. This is the reason for it. Cutting edge angles, if you have smaller cutting edge angles, if you go away from the 90 degrees cutting edge angles, you can compensate that with bigger feed. In the extreme, that's what we do with high feed milling. There we have cutting edge angles of 2, 3 degrees, 5, 6 degrees, 10, 15 degrees, anyway, far away from 90 degrees, and that gives us the opportunity, in a big number of cases, the obligation even, to use big feeds. Cutting edge geometries. Cutting edge geometries, you have sharp, you have strong. The two are kind of opposite to each other to make sure that both work, that both function with their full capacity. The feed needs to be modified as the average ship thickness should be different related to if you use a sharp cutting edge or a strong cutting edge. In the end, workpiece materials, depending on properties of workpiece materials, we have to be very careful with ship thicknesses, and that means also average ship thicknesses. On the one hand, that we don't have mechanical overload. Ships should not be too thick. But on the other hand, that we don't have thermal overload. Ships should not be too thin. So workpiece material properties play their role also in this comparison. And this one single slide, that's the, one could say, the practical conclusion of this presentation. Here you have the guidelines. Here you have the rules of thumb you can use during machining. And as I said before, don't worry too much about calculation. Today we have all the means needed to do the whatever calculations we want to do. Before you jump now very enthusiastic into the workshop and you start doing things, be careful, because as I said, my challenge is that I only have 40 minutes, 45 minutes, so there are a number of things I haven't been talking really about. But don't worry, if you go for things like the Suggest software, it's built in, these security things, because we have been discussing here a bit about equivalent ship thickness, average ship thickness concept. But there is also something to worry about at entry. When the cutting edge starts cutting, the ship should not be too thick, so you don't have too much of a mechanical impact. The ship thickness at exit should be not too close to zero, because you remember previous session we have been talking a bit about it. It should not be too close to zero, but it should not be too close to the center line of a milling cutter. So there are some considerations also. And of course, in all these things with increase the feed and reduce the feed, there is always the surface roughness of the machine surface that plays a role also. It's very nice to say increase the feed. But yeah, there are some constraints to respect when we talk about finishing. Average ship thickness. I hope I made it clear, the concept, the why we have it, the what we want to do with it. As I said, don't worry too much about the calculus anymore. That's a little bit old-fashioned. Today we have much more user-friendly manners to do calculations. However, we machining people, we still have to do the thinking. As I said, it's nice a computer, but a computer just gives you a value. The interpretation of the value in the today's world, that is still in our brain it needs to happen. Let me see about questions. Quite some questions again. First question, the speed of the inserts relative to the workpiece are higher. it's an explanation of my question in the beginning, and it's very correct indeed. The milling cutter moves in situation C faster, or you have the ability to move it faster, and that means that the distance to travel is the same. The cutter moves faster, so the time to do the operation is shorter. And when the time is shorter, that means that you have a more productive situation. Somebody is asking then, when having a thinner ship, does that influence the power? Yes, of course. A subject we haven't been talking about so far, but which is for sure on the agenda, the mechanical thing, cutting forces, cutting power, that type of thing. I would even say the question itself, it should not be a question, it's the ship thickness, the thickness of a ship that is determinative for the power of the operation. It's not the feet. Indirectly, yes, because to have a certain ship thickness, you have to modify the feet. But it's something, each time I try, when I'm teaching, I try to make people aware of that feet and depth of cut and those things are only of secondary importance if we start thinking about how a cutting edge is behaving. And the conditions a cutting edge is demanding for it to cut well, the power, the stability, all that type of things. I have to keep my eyes on the time, but I think we have one more question. Is equivalent ship thickness the same as average ship thickness? No. Again, average ship thickness, kind of, you can see it like this. Average ship thickness is not concerning the point of a cutting edge or of the point of a cutting tool. It's just the cutting edge. Equivalent ship thickness, however, focuses basically on the cutting point only. So it's two different things. The beauty today, the beauty of the work Søren has done is that he combined the two, he combined the two. He said, of course, the point is cutting, also in milling, so equivalent ship thickness should be on our mind. On the other hand, if you talk about cutting edges, average ship thickness should be on our mind, and he combined the two. Also here we had a bit of an issue with wording, how to call it, like always in machining, that's a bit of an issue. But it's for sure not the same. There is a question also, how does Vericut force optimization help level loads H1 ship thickness? I'm not sure if I understand the question. The only thing I can say is that force optimization in Vericut is, as far as I know, the concept, the model used in it is a somewhat modified Kinzel model, and that makes that it's Vericut force optimization is working with H1 values. So Vericut force optimization in this respect is, in my eyes, a very beautiful system. I don't know exactly what the question is, but as far as my interpretation of the question, the answer is yes. Vericut works with H1 ship thicknesses and as such is optimizing cutting forces in such a way that the cutting force is stable during machining. There is and that's the last question then, because I have to respect a little bit the time. If you exceed the maximum age set that a tool can cut, it means the tool, it will break, or what happens when we exceed it? Now, I'm a little bit tempted to say I do not answer this, because that's the subject for the next Getting Technical event, where we are going to talk about geometries. But that would not be fair for the one asking the question. So if you exceed maximum age set, yes, you break the tool. Perhaps not instantly, but in the long run, you will. If the chip thickness is too thick, you mainly in a mechanical way overload the cutting edge. And if you in a mechanical way overload cutting edges, you break them in the end. It can start with little chipping, little cracks being formed, but it will end up in catastrophic breakage. So if you exceed maximum age set, you break the tool. Yes, indeed. The remaining questions I propose. We take them in the comment, in the chat. All questions, I take the time needed to give you all the answers there. If there are more questions, of course, you can put them also there. Within the coming days, I go through and give you as many answers as possible to the questions. At the same time, also, I would like to invite you already for the next session, end of March, March 27, where we are going to talk about what I personally always refer to as the geometry factor in the machinability equation. Because talking about machinability, for some strange reason, people always like to discuss details and go around what is really important. And what is really important, so much underestimated still today, is geometry. People a million years ago already knew that geometry makes the difference. If you talk about a cutting operation, a machining operation. But that's for next time. For the time being, on behalf of my colleagues and myself, of course, thank you very much for being here, for listening. I hope it was an interesting hour. I hope you had some things to reflect upon, that you heard some things that could give you ideas on how to optimize, how to improve your milling applications. Thank you so much. Looking forward to see you at the next session.